In this video, I'm going to discuss how to use limit laws as well as graphs to help you find the limits to different functions. So first question, we have limit of a sum of two functions. So if you use the sum law, you can distribute the limit to be just of the quadratic and then limit of the log separately. Then what you could do is draw the quadratic and draw the log function. And then you will see that as x approaches 1, from both sides here, for quadratic, you do approach a y value of 1. On the log graph, however, you're approaching a y value of 0. And so using the limit laws, you could just say it is equal to 1 plus 0, which is just 1. Next question, we have a constant multiplied by a function. So this is the scaling law, that we're just stretching out the cosine law vertically by 7. So we can imagine that this 7 is not part of the variable x, so it could be pulled out of the limit. And then we could just draw the function cosine x. So this is a rough sketch. As x approaches pi, then the y value that is being approached here is -1. So by the law, we can have 7 is multiplied by -1, which is in the end -7. In this question, we're going to use the product law. So we're going to find the limit of the exponential separately and limit of the sign separately, and then we'll multiply the results together. Drawing the graphs, we'll see that the exponential graph grows here because this e is a constant number that's 2.718 roughly. So it's going to grow. And then the sine graph, this dotted version right here, is the parent sign without any transformations. And then we have x minus pi over 2. That means there's a shift to the right pi over 2. So if you take this value right here, shift it to the right pi over 2, you'd get this solid graph right here. Then we want to know what's the limit as x goes to 0. So on the exponential, we're approaching 1. That's the y value. On this sinusoidal one, we're approaching -1. So using the laws of the product, we can just multiply 1 with -1 and get -1 as the final result. For the quotient law, we have to be careful. We cannot do limit of the top and limit of the bottom unless the bottom limit does not approach 0, which it does not. So we can apply the quotient law here. So limit of the exponential separately and limit of the linear separately. So let's draw exponential growth graph and the linear graph. So because we're interested as x goes to 1, exponential is going to approach a value of 3. And the linear graph is going to approach a value of -1. So all we have to do is divide the results to get our final value. Next, we're going to use the continuity limit law. So in this particular example, because the outer function, which is the quadratic, something to the power of 2, is a continuous function, we can bring the limit on the inside of this quadratic and figure out limit of the absolute value function that got shifted down 4. Once we know that limit, then we can figure out what happens with the outer function. So drawing the inner function, we have absolute value -4, so that's absolute value graph that's shifted down 4. And we're interested in when we're approaching -1 on the x, so the y value being approached here will be -3. So then, using the law, we have to rewrite this as a limit as x approaches to -3 now of the power function of 2. And this picture is just a quadratic. And we want to find out what happens when we approach -3 on the x, and y values will approach +9. And so we have this result 9. And one more similar to it, we want to see if we can bring the limit on the inside of ln function. In case you weren't aware, ln stands for natural log with base e. So usually log function is, there's a base there, any constant. So in this case, the constant is a special number e, which is 2.718 roughly. So the logarithmic function is continuous on its domain as long as the input is positive. And because we have x going to infinity, then obviously we're going to be on the positive side. So that should be fine for us to bring in the limit on inside of the log, because the input will be positive as x goes to infinity. So all we have to do now is investigate what happens with 1 over x. So here's the graph we're interested in. As x goes to infinity, we're going to be approaching 0 here because there is a horizontal asymptote. So it's going to be approaching 0 from the top. So we're going to write down 0 with a little plus sign to indicate that. All the previous ones, we were always approaching from both sides, from bottom and from top. So we never had to indicate on this approaching x going to -3 from left or right, because here we're going from both top and bottom, so that was a two-sided limit. Here it is one-sided limit because we're approaching that 0 only from the top, so then when this output becomes the input, we're going to be approaching 0 only from the right side of this new function ln. So drawing the log graph, we will have that as we are approaching 0 from the right side, it actually will exist. If we didn't have this plus sign, the result would have been does not exist, because we don't have the other side of 0 for this graph. But because we are only approaching it from the right side, it actually does tend to -infinity. And so we can actually state that, even though we can't really reach infinity because it's not a real number. Last to discuss is about composition. So imagine one of the functions here is going to be a piecewise graph, which is a straight line with a hole at x equals 1, and that hole is actually filled in elsewhere at y equals 5. And then we have a very simple function, constant function g, which is constantly at 1. Our goal is to figure out what is the limit of this composition. So because the outer function f is not continuous, do you see how it's broken up at 1 here? Then we may not be able to just bring it in. Maybe not. So we have to investigate that a little bit more. So here is the main idea written down on the bottom. So if the inner function is approaching a specific value of b as x goes to a, then the result of this composition could be what we usually do, bring the limit on the inside and find the limit of the outer function, or it could be just the output value at the inner function approachment. It all depends on what the inner function g looks like near x equals 0. So if there is any horizontal piece there, so here it's purely a horizontal graph, so obviously that's the case in this situation. So let's look in detail what happens when we evaluate these three things, and then we'll discuss it. So first of all, we want to know what is the inner function approaching as we're approaching x equals 0. So the inner function is going to approach 1. So as x goes to 0, the g of function is just 1. Then the evaluation of the function at the 1 will be just 5. But the limit as x goes to this 1 of the outer function is actually 2. But it's approaching from both sides there. So what happens here? Because this statement is true that the inner function is horizontal, since g takes values of 1 near x equals 0, we have a flat graph, then we actually have this as the final answer to this composition, limit of a composition. So it would actually be 5, which is a little weird, because how can you get 5 if you have nothing to approach it on? But it will make more sense if we actually draw this composition graph. In order to do so, it might help to look at some table of values. So because we have to find out the inner function first and then the outer function after, we know that g is defined to be constant. So no matter what you get for the input, you always have to have an output of 1. But then if you're looking at inputs of 1, then the function value is always going to be giving you a 5. You'll never get this 2x for this composition. So the composition graph is going to be a flat graph at 5. And then if you're looking at what is it approaching as x goes to 0, it will definitely approach this 5 itself. Let's just do a few more like it, except this time we're going to be composing a function with itself. And so let's look at what's going to be happening with the inner function as x goes to -8. So -8 over here, we're approaching the value, y value of -6, but notice how it's both of them are coming from the top. So I'm going to be very specific that it's approaching -6 with a little plus sign. Then I'm going to think what happens now when we approach the outer function, which happens to be the same function again. So at -6 with a plus sign would be -6 approaching from the right side. So that's going to be over here, and it's approaching that 3 value. And that's it. Next, we're going to find out if the limit as x goes to -6 from the right side, what happens to the inner function? Well, this is approaching 3. That's the same one we just did. It's approaching 3 straight on. It's not going from the top or from the bottom. It's like flat there. And so because it is flat there, we're going to just say this is f of 3 itself. And f of 3, if you look at the graph, at 3 evaluated is actually the value of 5 again. So if you're having any flatness, just remember that there is no extra limit to do, just evaluate. One more. As the inner function, as x goes to -1 of the inner function, that's going to approach 2. So let's take a look over here. At -1 right here, we're approaching this 2 from both top and bottom. So because it's not straight on, it's just from top and bottom, we're going to rewrite this limit as x approaches to this 2 of this outer function now. And so when you look at that, here we have approaching 2 from both top and bottom again, and it looks like it's approaching a value of 3.